Hey everyone, welcome to the video. Today we're going to look at LeetCode 322. It's titled Coin Change. What are we going to do in this problem? We're going to solve this problem using a dynamic programming solution, in particular a bottom-up dynamic programming solution. This is a great first dynamic programming problem. It's very easy to code up in your own environment and visualize. There's no additional data structures. We're just going to use a Python list, an array in other languages, as you guys know. And so we don't have to have like any helper methods or anything like that. It's a LeetCode medium, really just because it has dynamic programming, but I hope you'll find the solution pretty straightforward and elegant. I'm not going to cover other solutions that are less efficient. For example, there are tree-based methods where we can recursively, either depth or breadth first, go through a bunch of different options. We're not going to do that. We're going to just jump straight into the dynamic programming solution. Okay, so what do we have to do in this problem? Well, we're told that we're given an integer array of coins representing different denominations and an integer amount representing a total amount of money. All right, when you see denominations here, do not worry. We don't have to have euros and cents and dollars and pesos. That's not what that means. All it really means is that there are coins with different values in a list. So pretty straightforward. And what we want to find is the fewest number of coins that we can add up to get to this amount variable. So down here, there's a lot of ways we could get to 11 with 1, 2, and call them dollars, $5 coins. We could have 11 $1 coins. We could have, 5 $2 coins and $1 coin. But it turns out the fewest number of coins that we need to get there is 2 $5 coins and a $1 coin. And convenient for us, we don't even have to return those coins. We really just have to return the number of coins that are needed to get to that amount. So that's really nice for us. One thing that could be tricky is that we're also told that it's possible that given the coins, we may not be able to get to amount. So this shows an example right here. Using $2 coins, we can't get to exactly 3. We could get to 4, we could get to 2, we can get close. We can't actually get to 3. A lot of times with algorithms, having to check for a solution not existing can be tricky. But here you'll see that the way we use the Python list and the dynamic programming structure to get to the solution, this kind of comes baked in. We don't really have to do any extra work. It's very, very easy. So I hope you'll see the elegance in that and enjoy it. And then finally, we're told here at the bottom that we can use an infinite number of each kind of coin. If that weren't the case, it'd be a little trickier. And I think there is a LeetCode problem, which I'll tackle in another video, also titled Coin Change Something, where we don't have an infinite number of each kind of coin. That makes it a little trickier, but we don't have that, and so this is going to be really straightforward for us. One concept I want to bring up real quick and just encourage everybody to go read, maybe after the video or something like that, or even right now, is the Wikipedia page on optimal substructure. Since we're using a bottom-up dynamic programming solution to this problem, it's important to understand cases when optimal substructure applies and also those when they don't. I don't think it's worth me going through right here. I'm only going to focus on the code, but I encourage all of you watching to go check this concept out on Wikipedia if you're not well versed in it. Okay, with that intro information covered, let's go ahead and start doing some programming. So here I've got coins and amount copied in from the first test case over here. Coins 1, 2, and 5 and amount 11. That should look familiar. To do this bottom-up dynamic programming solution, we're going to use a Python list, and I'm going to call that list mincoins. A lot of times you'll see this called DP, short for dynamic programming, obviously. In fact, you see that in a lot of dynamic programming algorithms, but I don't like that. I think your variables should be explanatory and informative, and if you just name a variable DP, it doesn't really explain anything. So I've named mine mincoins, and it stands for minimum number of coins. I can kind of show you what I mean by that. The way we're going to build this out, which we'll cover in a second, is we're going to have every element of minimum coins represent the smallest number of coins needed to get that sum. And by that sum, I mean the sum of the position or the index of the list. So let me show you examples so that's really clear. Position 0, we don't need any coins to get a value of 0. So 0 would be the ultimate value here. Position 1, we have a $1 coin, so we can get that value. Same with a 2, we have a $2 coin, we only need 1 coin to get that, so we can have the entry of 1. Now position 3, there's 2 different ways that we can get a value of 3, a 1 and a 2 or a 2 and a 1. Ultimately though, that takes 2 coins, so the answer there is 2. Now position 4, a little trickier, right? You know, we could take 4 1s, we could take 2 2s, we could take a 1, a 2, and a 1. Ultimately though, I hope you can see without going through the proof that the quickest way we could get to 4 would be to use 2 different coins, and then when we get to 5, we're back to a value of 1 again. So that's what that list is going to look like. And again, I'll show you how we'll build it out in a second. How we build that list out is really kind of the core of this algorithm. How we initialize it is also important. So right now I've just initialized an empty list. That's not what we need to do in the code. What we need to do is we need to initialize this list with some kind of really large value in every position. And we need to do it for the length of amount plus 1. Why length of amount plus 1? Well, we need to find the minimum number of coins needed to get to every position from 0 up to the input amount. So to do that, that is the length we need. Now, what kind of value do we need to put inside minimum coins? Well, we want a really large value, or at least a large enough value to where we could never have the wrong answer in that position and not know it. So some people will use like math.infinity here. What I want to use actually is really just amount plus 1 again. And the reason I'm using amount plus 1 here is that we're told with the problem that the minimum value of coins is 1. And so if we have a coin of at least value 1, there's no way that we can get to a number of coins needed that's greater than the max amount plus 1, right? Imagine if the value we're trying to get is 5. We can't use 6 coins to get 5 if we're told that coins always have at least a value of 1. Again, I hope that's kind of self-evident, but you know, if it isn't, maybe just write down some examples and you'll see that you really need fractional coins to get that. Now, you know, this isn't super necessary, but whenever I see repetition, I like to create a variable. So I'm actually going to create a variable here called max value, and it's just going to be amount plus 1. Very simple, but again, that makes me more comfortable, and that's how I like to code. So I'm going to put in max value here and max value over here. All right, let's make sure this works before we move on. Comment that out, run this. You know, let's actually take a look at min coins and make sure it just looks like the way we think it should. Okay, and it does, right? We've got that max value of 12, which is 1 more than the amount that we put in. And yeah, it looks like it's got the right length. Okay. Now we got to get into the main meat of the program. So we've kind of got our core data structure set up right here. And we need to basically iterate through the problem space now and put meaningful values in here. Because right now we don't have actual answers for what the shortest number of coins needed to get to each one of these positions is. You know what? We do have something missing. Remember, we said that the 0th position needs to be 0. Let's actually put that in real quick. Min coin 0 is equal to 0. All right. Now that we've got our 0th position, normal back out, we can get back into the meat of this program. So, like I said, we've got the data structure set up. We just need to get through the main algorithm right now, and it's really straightforward code. So, as I've been saying, we're going to loop through all of the different, forgive me while I type here, loop through all of the different subamounts, all of the different sums that we can use on our way to try and get to the total amount, to, in this case, literally the variable called amount. So what we want to do is we want to loop through all of those different, as I'm calling them here, subamounts from 1 up to max val. And I'm using max val here, not amount, because we want to be inclusive of the largest value. And if we put amount in, the way these range loops work, that wouldn't work. So we need to go 1 over that. And then for all of those different subamounts, we also want to look at all of the different coin options we have. And basically what we want to check is we want to look backwards. We want to say, at this subamount, if I go back to a previous subamount using this coin, is there a more efficient solution? And so the first thing we have to check for is if we take our current subamount and we subtract the current coin that we're on away from it, do we get a value greater than 0? If we don't, the math didn't work out, we ended up at a negative value, and it can't help us because we'd be indexing on something in our min coins array that it might actually technically work. You can put a negative number into the index of a Python list, but then it works from the back of the list, and that isn't what we mean to do here. So we got to make sure that this look back here gives us a value greater than or equal to 0. And if it does, we want to find out if we found a more efficient, a shorter, a quicker, a fewer coin solution to that sub problem. So we're looking at that sub amount, and we're checking to see if the current solution, the one that we're looping through right now, is somehow more efficient than the previous one. And you'll allow me to type some code here, I can explain it. Okay, so we can go through that code again. By the way, I found a typo. Notice I'm adding nothing to this value right here. We need a 1 here. We can talk about why that 1 needs to be there. I know I went through that code pretty quickly, so one more quick overview. As we go through all of the subamounts from 1 up to our amount value, to the goal that we're trying to get to, and then we go through all of our coins at each one of those, we make sure that the difference between subamount and coin is positive or 0. And if it is, then we check to see, by using this coin and going from a previous solution that we know was the most efficient. So remember, anytime we look backwards in this array, we know that position that we're looking to was the most efficient one. Because of the way we're building is from the bottom up. We start with 0, that's the most efficient. Then we find the most efficient value for 1 and 2 all the way up to the end. And we check to make sure that if we use a coin from this current position, is that more efficient than the value we currently have in subamount? So by the way, as you can see up here, the first time through, that's always going to be 12 in this case, a very large number. So the first time we do this, we're going to get a new value, but sometimes we won't. As we go through the different coins, this may not happen. And many times when we go through the coins also, we won't even enter this final logic here because we won't get a value greater than or equal to 0. If you're wondering where the +1 comes from, I forgot it. Maybe I'm wondering too. I know I'm not. It's really simple, which is just that if we use a coin to go from our current position back to a previous one, and it is more efficient for the current sub amount, well, we need to include the fact that we're now using an additional coin. If I work out some examples by hand, that'll be really clear. But consider, for example, our example we built out up here. So we're at 1, 2, 3, 4, 5. If we're at 6, right, and we originally had the value of 12, and we're looking at the first coin, so coin 1, and we look back here, we find that if we just add 1 to the value that was at 5, we can get to 6 with 2 coins. But if we didn't count that 1 coin that we're using, the value we put in here would be 1. Instead, it really should be 2, I think. Let's run this and find out. I think we should have a value of 2 there. So we can print out min coins and make sure that there is a 2 there. Let's see, 1, 2, 3, 4, 5, 6. Yeah, there is a 2 there. Okay. By the way, this is the whole solution. Our final, the last entry in the list should be the return value. Let's make sure that we get 3 for that test case. Okay, we do. Sweet. There's one final bit of logic here, I promise, the very last one, and that is we have to account for the case where we need to return a -1 when there is no solution. And the only time that's going to happen is when the final value here never gets overwritten. We never find a more efficient path here. Basically, we never enter this final loop for the final sub amount. And so the way that's going to look is that the very last value, if we index on amount, because that should get our last value, that's what we want to return as long as min coins amount doesn't equal that max value that we initialized everything with. If it does, then we don't want to return the value we get from the final index. We actually want to return a -1. And to test this real quick, we can go back over to LeetCode and look at an example. So we could have crafted one of these, but might as well grab one of theirs. Let's see, if we only have one coin of value 2 and the amount is 3, we should return -1. So yeah, let's comment this out and just put in a new one real quick. Coins and amount are equal to 2 and a value of 3. So if we run this and then we run that and then we run that, we get -1. And that makes sense. Just out of curiosity, let's see what the whole min coins looks like. And that again looks right. Right, so I've copied this code over now to LeetCode, and you can see my solution here. It's fairly efficient. I don't really know what to tweak for this runtime stuff. You know, some of this is random. Maybe we didn't need to use max val. That would really be a memory thing. You notice the memory is about as efficient as you can get. Yeah, feel free to tinker with that, and if you guys find a way to boost the runtime a little, let me know. Maybe there's something we could do here. Otherwise, thanks for watching the video, and come back soon for another algorithm.